The infamous Young's double slit experiment is a very natural starting point to look at the second half of the Waves Optics and Acoustics module. So here's a brief guide to some of the key takeaways from that experiment. In the early 19th century, Thomas Young sits down at his desk in Germany to try and outwit a certain famous Isaac to prove light is in fact not corpuscular, but propagated the universe as a wave. He sets up the following experiment. A wavefront of monochromatic light consisting of well-defined wavelengths from a single source passes through two narrow slits. The light starts from here and then passes through these two slits, slit 1 and slit 2, or apertures. These slits are separated by a distance d between them. After passing through the slits, the light recombines behind the screen at a distance of L away from the screen. At the point they reconverge, the light interferes and an interference pattern is observed. This goes against the classical particle notion that the light would just form two lines directly behind the screen. First state that we are working within the Fraunhofer limit. This is a limit that simply states that the screen is far enough so the distance L is big enough that the two rays coming from slit 1 and slit 2 are parallel. So the Fraunhofer limit is essentially that the rays are parallel.
So we want to look at the path differences and see if we can actually get d sine theta when L is much greater than y and d.
So we start by looking at the individual path lengths themselves. For the bottom one, it's this expression. For the top one, it's that expression. And the path difference is just, the bottom one, the longer one, minus the top. Very simple maths. This is all just Pythagoras' theorem, trigonometry. Very easy. So I'm just going to breeze through it. Now, this path difference still doesn't look anything like d sine of theta. So how are we going to change it? How might we simplify it? Well, we start by pulling out a factor of L, which gives us this expression. Again, this is very simple maths. When you pull out an L, because you're pulling out the square root, you divide everything in the square root by L squared. That's how you get these two expressions. But again, this still looks nothing like d sine theta. So how might we get somewhat closer? How might we make some progress? Well, we do that by using Taylor expansions. So we can use the Taylor expansion rather, the square root of 1 plus x, rearrange or re-express rather both these square roots in forms without the square root themselves. However, it's worth noting that this Taylor expansion, the square root of 1 plus x, relies on x being much less than 1. So the Taylor expansion, the square root of 1 plus a variable, is 1 plus that variable divided by 2. So what do we get? Well, for the bottom ray, the ray that travels slightly further, we can express that as this. For the top ray, the ray that travels slightly less further, we get 1 plus y minus d over 2 squared divided by 2l squared, all multiplied by l. So this is what we have here, expressed slightly more nicely. When we put these two values into the equation for path difference, just r2 minus r1, and we can see quite quickly that the path difference comes out as yd over l. Looking at this expression, we can clearly see y over l is tan theta, but remembering that y is very small and l is much larger, we can use small angle approximation and say that tan theta is equal to sine theta, which is equal to theta. So now we can essentially say, because this angle is so small, theta is equal to y over l, and we've verified that one of our objectives of proving that theta was a very, very small value. Now we need to prove the path difference is equal to d sine theta. Well, if you look at the equation, we had r2 minus r1 is y over l multiplied by d. Well, we can see that y over l is equal to tan theta, which is equal to sine theta, because the angle is so small. Replace y over l with sine theta, and you have r2 minus r1, i.e. the path difference is d sine theta. So both the objectives that we needed to prove, i.e. that theta was small and that the path difference with d sine theta have been verified.
Another thing that we can see from the diagram is the path difference between the wave coming from slit 2 and the wave coming from slit 1. So we have the path difference as being this portion of extra travel that path 1 has to do. And this, from trigonometry, can be seen to be equal to d sine theta. Some assumptions we make to make this the easiest possible case is that there is no phase difference between the light coming from the top slit and the light coming from the bottom slit, and that both sources of light are of the same amplitude. So the light coming from slit 1 can take the form, and the light coming from slit 2 will take this form, where the delta is equal to kd sine theta, or simply the path difference between these two. So with these preliminaries established, we can write the total amplitude given at point P as the sum of these two, or in other words, Immediately we see that we can take out a factor of e from the right hand side, and we end up with this. And then again, the e's will cancel here and here, so we end up with the total equation for the amplitude of the wave at point P as being the following. Furthermore, this can then be divided again by a factor that will allow us to use the Euler formula later on. So if we take out this factor,
We see that by using the Euler formula,
we can rewrite the top equation as simply, or if we wanted to put it more neatly, it's simply